Hey everybody, my name's Jordan Smith. I'm one of the online students, so I don't think I've ever met any of you, but I live in Augusta, Georgia. I work at Savannah River site for the Savannah River Tritium Enterprise. Um, it's a lot of fun. If you've never been, I recommend you try and go out there, get a tour or something. Um, a lot of good nuclear engineering opportunities out there. This is my presentation on flywheel energy storage. What are flywheels? You can see the picture. It's kind of a little diagram of a flywheel. Essentially, it's a vacuum enclosure with a rotor inside that an electric motor spins that mass around in the motor super high speeds, up to 20,000 to over 50,000 RPMs. So extremely high speeds. There's a bearing on each side. Uh, the top and the bottom of this rotor that connects it to the actual housing. The entire flywheel assembly is mechanical. There's no electrical or any kind of parts like that going on, no chemical, um, you know, like you'd see in typical batteries. All the energy is stored as rotational energy. This is kinetic, more commonly known as, um, and extremely robust and high quality materials and applications. You can see up to 90% efficiency, um, which is very good for mechanical. Um, some of the background, the science behind flywheel theory. Um, you have rotational energy, kinetic KE is equal to 1/2 of inertia times the square angular velocity squared. So it's very similar to a standard kinetic energy equation that you're used to. Um, with this relationship, you can see that you can increase your energy output by either increasing your moment of inertia, getting a larger mass, or raising your angular velocity by raising the speed. Um, most more of the larger flywheels, you'll see a much larger mass without having to raise the speed as much, which increases safety for everyone around it, even though failure is extremely low in these type of applications. Um, this this method of energy storage and flywheels essentially works as a battery, even though it's completely mechanical. So it's kind of a one of a kind in that aspect. The argument for using flywheels, as you can see in the bottom of this chart, high power flywheels take only seconds, sometimes milliseconds, to actually dispel the energy that is stored within them. So you have an extremely high power density, extremely high energy density, all the way up to about a megawatt for common high power flywheels. Um, Another big advantage that flywheels have over other battery types is that being completely mechanical and only having two bearings really taking the load of this energy transfer over and over. Most flywheels are guaranteed reliable up to 10 to the power 5, 10 to the power 7 cycles. Um, there are actually some flywheels to this day that have been running for over 200 years. They're extremely reliable, so that leaves you with relatively no maintenance for 10, 20, 30, 40, 50 years, as a setup to over 200 in some scenarios. Um, Another advantage flywheels have is the high power density. They're extremely useful for when you need a whole lot of power in a very short amount of time in a very quick burst. So I'll show you some of the applications where it's most useful. One example is roller coaster down in Universal Orlando in Orlando, Florida, the Incredible Hulk roller coaster. If you're not familiar with it, it is this large green roller coaster in the bottom right. The other image is the tunnel where liftoff, where you have the typical chain pulling up a roller coaster to where the roller coaster peaks and falls by gravity throughout the remainder of the ride. But in this scenario, the Incredible Hulk, they designed to have the car slowly coasted up this tunnel you can see right here, and instead of falling by gravity, this roller coaster is actually powered by 4 flywheels, which launches the cart 30 degrees up to 0 to 60 miles an hour in 2 seconds. And the only way to get the amount of power it takes to actually get that cart going that fast at that angle at that speed, it was 8 megawatts per launch. And if they were to do this off of just basic traditional electricity and batteries, that it would cause the entire city of Orlando, the entire grid would brown out after every single launch. In order to get around this, they use multiple flywheels that can store this energy and easily power this ride without any loss to the power grid. Another example, this is the same picture you saw on the cover slide, and this is from NASA, is a G2 flywheel that they developed back in the early 2000s at the Glenn Research Center. And the reason this flywheel got so much publicity is because it was one of the first ones ever built with aerospace grade titanium and carbon fiber elements, and instead of using 2 mechanical bearings, they implemented the use of electromagnetic bearings to where the rotor inside is actually levitating and not touching any parts. So this flywheel could theoretically run forever without ever breaking down or ever needing maintenance done to it. This specific flywheel also gained a lot of attention because it was designed to have rotor speeds of over 60,000 RPMs. This means that they could use a much smaller mass inside, no larger than about 250 pounds. And NASA is furthering developing this technology to see how it can hold up. Some other applications they've been using flywheels and experimenting with, you have the picture in the bottom right, which is a rail gun, very similar to laser weapons developed by the Navy and the Air Force. These weapons are very primitive right now. They are not mass-produced, mass scale, or anything like that because of the experimental flywheel technology being played with. Essentially, these weapons require extremely high bursts of energy all at once, and in order to get that kind of power without completely destroying a power grid, you need flywheels. Another big application that is more mainstream is aircraft powertrains and aircraft launch systems for aircraft carriers. The technology used here, for example, the Gerald R. Ford is an aircraft carrier, and in order to launch aircraft off of its deck, they have 4 rotors each that are capable of over 120 megajoules apiece. So those combined, you're close to 500 megajoules to where they can launch aircraft. These 4 flywheels together take about 45 seconds to store up 500 megajoules of energy, and it takes less than 2 seconds to release all of that energy into the planes. Another application that's non-military is the CVT, which is the continuously variable transmission. These are essentially being used, as you might have see in the electric cars like Tesla. They have regenerative braking. So actually when a car is slowing down, the flywheel starts storing this braking energy, and when the car begins to accelerate, these flywheels kick in and are drained again to power the car's acceleration, have a more powerful and clean acceleration. These CVT motor transmissions actually were used not too long ago in the 24-hour Le Mans race in Europe, and the hybrid Porsche and Audi that won the race was actually using CVT transmission. So that's pretty impressive. Here we have another graph that shows you your energy storage systems by duration and power. Down here near the bottom, you see the supercapacitors, lithium-ion batteries, and right between that is flywheel storage devices. This again, it is the quickest mechanical storage system by far, and compared to electrical, you actually get a little bit more power capacity than the other two below it, but you also sacrifice a little bit of charge time. This is helpful for various different applications where supercapacitors and SMESs are not exactly what you need. Flywheels are there for other applications. Here's another chart. It's a power density versus energy density grid. You have supercapacitors, capacitors, you have rechargeable batteries, you have your ICEs, your engines. And right dead in the middle is your conventional flywheels. These are going to be the roller coasters, the CVTs. Then once you get the more advanced flywheels up in the upper right hand corner, you actually start to see an extreme advantage of the advanced flywheels compared to supercapacitors when it comes to your energy density. Compared to rechargeable batteries, there's an obvious power density advantage, and that's why advanced flywheels are being developed by NASA to be used on a broader spectrum and not just in transmissions. And then, since flywheels are considered batteries essentially in nature, when compared to electric batteries, they actually have advantages. Some advantages are, compared to batteries, flywheels are not affected by temperature. They can affect just as efficiently in extremely cold temperatures as well as extremely hot temperatures. As compared to chemical batteries, there's no environmental threat, which, depending on who you ask, this is an extreme advantage. You don't have to worry about environmental regulations, the EPA. You don't have to worry about, in the event of a failure, is this going to cause an extreme damage to the environment or the humans around it? You don't have to worry about anything with that with flywheels. Another advantage you might not think about, or might not be as readily apparent, is that it's very easy to figure out how much energy is stored within a flywheel by simple calculations of the mass of the rotor and the speed of the rotor. There's no second guessing, there's no estimates. There is an exact number of energy stored within this flywheel at all times, and you can figure that out. And the obvious advantage is the lifespan. As I said before, there are some of these that are over 200 years old, and when you get into the higher grade flywheels, there's no maintenance, there's no mechanical failure threat. They'll last forever. On the other hand, electric batteries do have the advantage in the sense that when energy storage is needed on a custom appliance, underneath a car, on a train system that needs to go through a tunnel, you can't stick a flywheel just anywhere because a flywheel has a fixed volume, a fixed area. They cannot be manipulated as much as a set of batteries. Batteries can be configured, designed, and relocated any way you need them to be. I think that is why batteries, you see way more battery technology in today's applications than you do flywheels. If you have any questions, again, my name is Jordan Smith. You can reach me at this email. And I look forward to hearing from you all. Thank you.